Hello, my name is Pavel. I represent Team PV and I want to talk about our models that we prepared for FinRL context on a task for digital regulatory reporting. We worked together with my wife, Anna, and our idea was to try out the mixture of expert architecture and to stay within a reasonable budget for this project. So the model, the task has three domains: common domain model, model openness framework, and XBRL. They are incrementally more difficult. The first part is just a Q&A. The second part has license abbreviations and license approvals. And the last part is XBRL, by far the hardest. It has a financial mass in it and has a number of different queries to the XBRL reports. It had the FinRL, and which is a tag classification, and it has and some questions about the companies in the DO 30. So we decided that we'll spend most of our effort on the first two tasks and ignore the last task for most of it, because like a marginal contribution to the result, they're all equally weighted, and the marginal contribution for the result from the specializing on the third task is not that great compared to the first two. We, for the Q&A tasks, we just downloaded documentation and created a question and answer data sets of this format. So using DeepSeek, so we wrote instruction, feed it a chunk, and it produced a Q&A, which is a fairly standard way of doing this. For license abbreviations, license FC approvals, the challenge is these data sets are very small, it's like 50 license approved, so we created some false examples and a number of templates to like play around. So is it approved, is it not approved? Do you know if this license is approved by blah, blah, blah? So just a different phrases of the same question, and and false and true examples, and the same for abbreviations as well. So they are like a templated. Q&A is the same approach as for CDM, just download the documentation and feed it into DeepSeek. For the financial math, we couldn't find any good financial math questions, so we created our own. We created a list of the topics. So for CFA curriculum mainly, and asked DeepSeek to iterate through the topics, and for each topic, subtopic, create 5 questions and answers. And we use that as a material for training our model for math. We also use a ConfInQA dataset, only a part of it, because it's very long and it didn't fit into the memory during training, even with batch size 1. So we have to only use about 20% of it, which is like a 1500 character questions. Next is our model architecture. Model architecture was a bit of a journey for our team. So we started with the idea to have 3 experts. So we wanted to train 3 models, 3 billion parameter models, and then squash them together into one model, and then trace them 3 together, hoping that they will share the knowledge somehow. And this is not the case. How this actually works is the layer, even though we were careful to like not train the shared layers and so forth. So what happens is that the first layer, it expects to have a certain configuration of the deeper layers. When a router didn't route the first layer to this state of like other expert layers, so let's say the model 1 routed to model 2, routed to model 3, and so forth for 24 layers straight, we got gibberish. And that's exactly what happened. So there is no magic. The router doesn't know where to route. We can't train it. It's impossible to train. And even if we start training it, like it just regresses. It doesn't regain this cohesion. So we pivoted into a simpler model. So we wanted to start with a baseline. So we wanted to avoid the initial training, which is long and expensive. So we took an existing model. An existing model just happened to be Qwen from Chinese Alibaba. So they released a MoE family of models, and they have also Instruct family of models, which are very similar architecture, which is convenient. So for the MoE family of models, we put 16 experts in every layer, no shared layers, but the shared expert and a top 2 gate. So the top 2 means here it talks to one of the experts and the shared expert all the time. So there is no like expert collapse in this situation. And because all the other components like attention layers, input, output are same with Instruct, we were able to seamlessly transfer the training data from small Instruct model onto this one. And this is how we done it. We took the base model, loaded it, then we took just the configuration from the target model and we modified intermediate layers to match. Because by default, the MoE models have like a smaller expert layer dimensions than the Instruct models. And like the shared layers are wider and the expert layers are narrower. However, in order to transfer the knowledge, we have to have the same dimensions. Therefore, like we expanded the sizes. And we loaded it. It's not a trained model, but still it throws a lot of errors because it can't like mismatches in the dimensions basically. So to address this, we traverse through the layers. We copy the weights from the experts because MLP in feed-forward layer is the same as the weights, the configuration is the same as the expert configuration inside the MoE layers. So we can just copy that as is. And a router is initialized randomly. And so what happens, it doesn't matter where a router routes because all the experts are the same. We got the same result as if we were talking to the base model, which is great because we don't have to train the base now and we can just enhance this model. So we can do fine tuning. And one of the challenges there is that the fine-tuning for MoE models is it can't use LoRa, so it can't use adapters. So it has to load all the model weights into memory and all the optimizer weights. It is very memory intense, and we didn't have access to 800. It is also a bit expensive, so we try to stay like under the radar, and like it's not straight up available from Hugging Face, for example. It is like a special contract you have to enter. But we had a 40S GPU, which we rented, and it is 48 gigabyte of memory. So we had to cut down number of experts to 16, whereas another model is 5 billion parameters and not 8 billion as allowed by the organizers. But well, due to hardware constraints, we just couldn't make this happen. And here is our results. So we have a CDM and basically all the Q&A, CDM and MoF are not that great. It's worse than the baseline. We spotted this late in the process and we were able to enhance the results quite a bit. Because the base model is small, so it can train on small data sets. It has really good data retention, and these tasks are basically documentation questions. And I reckon it would be possible to achieve good results with this architecture on these two tasks, but we didn't have a lot of time. We have like 2 days left when we uncovered that this is happening due to all our troubles with architecture. Then license abbreviations and license approvals were very good. The expert specialization worked and kind of it proves it. so this data remain intact. And whereas for the baseline model which we trained, which is Quen 7b, we were unable to achieve nowhere near these results. They can't remember the approval status for some reason. And that was like all the previous competitions, that's the same results. For the XBRL analytics, like all the credit goes to the author of LanXC. So all of XBRL results come from this data set. It's a good data set. And the financial math, not great but we didn't spend a lot of time on it either. For effort, half of the time is data sets, and the remaining time is about 3 equal parts: the architecture, then the documentation, writing articles, and then the paper, and then the final stage where we iterate and recreate data sets, retrain the models, run evals. And the budget, $80 for compute, $40 for API. We use OpenAI for eval, we use DeepSeek for everything else. Well, as you know, DeepSeek is very cheap, but it is also very slow. And in later stages, we were running out of time, so eval was done by OpenAI, so we needed eval results quick. So thanks for listening. Bye. Мне кажется,